Yesterday we started discussing about design under uncertainty. So that was a new module that we started, if you want to say it like that or think of it like that, where now we are not only interested in analysis, but we are interested in how to use that analysis to design components, design systems, to design product, and so on and so forth, right? So in this part, we will be talking about, as we started yesterday, about algorithms that allows you to design while incorporating uncertainty that is evidently there in the system. You are not introducing it, it is there, right? And we are talking about it in a broad sense. We talked about two primary types of algorithms for design under uncertainty, at least the big picture overview kind of thing. The first one was what was the first algorithm we discussed yesterday? Our first group of methods, reliability based design optimization, or RBDO. The second one we discussed about or we mentioned was robust design optimization, which is RDO, right? RBDO we looked into the at least some problem statement. RDO we did not look into the problem statement, so we'll do that today. But to quickly recap, this was the problem statement that we talked about yesterday, the bottom one, where you are trying to minimize a cost, let's say cost of construction and cost of manufacturing and all those things, subjected to a probabilistic constraint, subjected to a reliability constraint, to be more specific. So the idea is I want to design, which means I want to minimize my cost of production, my overall cost, while ensuring that my system is probabilistically safe, or my system is safe with certain probability, or it will fail with a very low probability. That is the whole idea of reliability based design optimization. So that left top that you see on the screen, that is the deterministic optimization, DDO, deterministic design optimization, where you try to minimize the costs subjected to certain deterministic constraint. For example, the stress should not include some threshold, the maximum displacement should not increase certain threshold, and so on and so forth, right? That is a deterministic setup. In the RBDO setup, what do we say? We want to minimize the cost given that probability that the stress will be greater than equal to some threshold is less than equal to a very small failure probability, right? 10 to the minus 3, let's say. Similarly, probability, a second constraint, that the maximum displacement will be greater than the maximum allowable displacement based on some codal provision. The probability of that is less than equal to some small number, let's say 10 to the power minus 4, let's say. And that is kind of the problem statement that you will deal with in reliability based design optimization. Why is it challenging? Because by definition it's a nested loop that you are working with. There is an optimization loop, the outer loop, and for each optimization iteration you will be solving a reliability analysis problem. So that makes it quite challenging, and that is just one of the challenges. Other challenges will come later when we talk about RBDO in details. For example, if to compute it using some gradient based optimizer, you can imagine you need to compute the sensitivity, which is the gradient of the probability of failure, of the probabilistic constraint. How will you compute that? You're looking at the constraint is a probabilistic one, you need a gradient of that. That will be challenging, you can imagine that. But we are not going to talk about that today. How will you compute a gradient? Gradient of a probability measure. Your constraint is what? Probability that displacement greater than equal to some epsilon minus some epsilon 2, which is 10 to the minus 3, is less than equal to 0. This is your constraint, right? So you need a derivative of this probability thing. What is derivative of a probability? How will you calculate that? Obviously, analytically you cannot think. I'm quite sure of that. Numerically you are imagining, but numerical has its own problem, right? So that is there. We'll not go there today. We'll not talk about our video today, but just giving you a glimpse of what is going to come maybe in the next lecture. Okay, so that was our video. In our video, there is one more thing that we talked about, which is, if you look into the screen, sorry, not this one, I want this one. So in a deterministic design optimization, I told you that in most cases, almost all cases, the optimal point will reside on the constrained boundary. The boundary, the contour of the constraint, that's where the optimal point will reside. And as a result, if there is some form of uncertainty, even a slight one, there is a very good probability it will go to the failure zone. It will become unsafe, because this point that you see, this is the unsafe zone, so this is on the boundary. Very easily, little bit perturbation, it goes into the failure zone. In reliability, the optimal value moves in this direction. So it is not on the boundary any longer, it is some distance from the boundary. So that now the probability of failure is much less, this area, right? This straight area, the darker brown area covered by the circle, right? And that is kind of less probable. That is there, and we talked about it, right? And that's fine. So now let us go to the other one. We started discussing about it yesterday, but we did not complete it. So the other form of design under uncertainty that we started discussing is the robust design optimization, right? The other form of uncertainty that you want to design, the other form of design and the uncertainty is the robust design optimization. Can you remind me what is the objective in robust design optimization? What are we looking for? The objective function. So we are looking at insensitive design. We are looking at a design point which is insensitive. So basically, which means that a design point, a perturbation in which will not influence the objective function in a significant way. There will be some influence, but not in a significant way, right? So that is kind of the idea. And so basically, if you remember the diagram from yesterday, this is the diagram that I was drawing, right? Let's say something like this, right? This is what we are drawing. What is the optimal point? We said discuss that. This is the optimal point, right? But the problem is that you give a small perturbation, there is a huge change in the y-axis. So this is your cost function or objective function. Let's write cost function, and this is your design variable. So even a small perturbation in the design variable, which will eventually come because of manufacturing uncertainty, it cannot compute it or design it exactly, your objective function changes significantly. Not desirable. A better design point, as discussed yesterday, is perhaps this one, where you give a same kind of perturbation, y-axis does not change that much. So it's more of a robust one, right? And what happens beyond that, we will come to that later, because I intentionally draw it like that, because I want to go there in some point. Okay, so this is more of a robust design. Even if there is a small change due to manufacturing or during manufacturing, your y-axis, the cost function, do not change, right? The cost function remains as it is, correct? So now, this is all good in drawing and schematics and all those things, but how do you actually solve it? What is the problem statement looks like? So let us rewrite the deterministic one first, the deterministic objective function. And from there, let us see if we can arrive together at the objective function, at the constraint, at the problem statement for robust design optimization, right? So let us first write down the deterministic one and let us try to arrive at the objective function for RDO together. Okay, so let us try. So for DDO, right? So first let us talk about DDO, and this is nothing new. It was there in the previous slide, it was there in yesterday's lecture. We know that here the thing is that D star is equal to arg mean D C D, and if I am more generic, I will write X also, subjected to the constraint, right, the deterministic one, H D comma X is less than equal to 0, and one more thing is the lower limit and upper limit. So D lower limit less than equal to D less than equal to D upper limit, right? This is the deterministic optimization problem. This is a DDO setup. This is the objective optimization problem that we must have seen somewhere in our life at some point, right? So now, remind me, what was D? Design variable. What was X? The variables that are not, we are not designing for, we cannot design for, but are random. So X are like the only random, the variables that are random. D is the variable that we are trying to control. It can still be random. In RBDO setup, we did not consider it random, but it can be random. But at the very least, it is, it is something that we are designing. So it is changing from iteration to iteration, right? What is H? Some constant, right? C can be cost, H can be stress, displacement, deformation, something like that, right? And then you have the bounds, lower limit, upper limit of the design variable, and that is always there. Okay. So now I want to convert it into a robust design optimization problem. We want to convert it into a robust design optimization problem. So tell me, what will be the problem statement? So now we are interested in RDO. Okay. So to start with, let us make our life simpler. Not that it will help much, but let's do that. So D, the uncertainty in D, let us ignore it for now. Although you cannot ignore it because that is the whole basis of this. But let's say the uncertainty in D is not there. D is some manufacturing error, but we are not modeling it as an uncertain parameter. Okay. So we are only interested in the uncertainty in X, let's say. So what will the objective function look like? First of all, what will you minimize? So previously, you were minimizing what? The cost. Or maximizing, let's say, the performance or something like that. So in this case, what will you minimize? What do you mean by deviation? Minimize the variance of the cost function. Everyone agrees we should minimize the variance? Is there someone who disagrees? I disagree, but is there anyone who disagrees? If you minimize the variance, don't you think I will arrive at this point? I draw it for some reason, right? Zero variance, right? If I only minimize the variance, I will arrive at that point. But perhaps you don't want that point, right? So what should I minimize? Minimize the cost. Which cost? Cost is C function. C is cost. So we should only minimize the cost. But you don't have one cost now because C is now uncertain. X, it's a function of X. X is random, so C is random. So what will you minimize? Mean. How many things mean? Mean and variance. So there is one. You are saying mean and variance. Anyone else? Only mean, is there anyone?
it should be within certain limits. In that constraint, mean should be minimal. Lagrange multiplier.
But then that's not a RDO problem. Because how do you know in what range is a meaningful range? Reliability, you know that what is a reliability. For variance, you do not know that. You will never know that how much is the uncertainty. So you can never hope to find that. And if you give some arbitrary number, maybe that is not a valid constraint. You will always never get a design convergence. So that you cannot decide. So what should you minimize? Someone said mean and variance, right? Two of you at least said. Let's go by that for now and see. If I want to minimize mean and variance, I have two objective functions. Do you know a setup that can handle two objective functions? Whatever we are discussing with for dealing with one objective function, right? But now you have two objective functions. One is the mean, other is the variance. What will you do? Max mean, you want to maximize what? The mean or the variance? What do you want to maximize? Nothing. Both you want to minimize. Negative mean and positive variance. And then what will you do? It's still two objective. You want to minimize mean and variance, two objective. You want to maximize negative mean and minimize. It's still two objective. Is right? There is a group of algorithms known as many objective or multi-objective optimization algorithm which can handle multiple objectives. But we are not going there, by the way, we will not do that. But that is a potential solution, so he is correct, right? There are class of algorithms that deals with many objectives, because in life we are always balancing between objectives. It's never that we work for one objective. We want to minimize our effort but maximize our grade. That's two objectives, right? At the same time. So we are always working. Yeah, go ahead. Yeah, that is one way of looking into things. The problem is that because D will also be uncertain at some point. So the second derivative gives you the sense. The first derivative actually gives you sensitivity actually. So that will be done by variance, and we'll cover sensitivity separately at some point. Where we'll talk about different ways of computing sensitivity. So in probabilistic sense, just as a one-line kind of thing, variance-based sensitivity is a thing, where variance represents sensitivity in that sense. So that's when I say insensitive design, I mean you're minimizing the variance only, okay? Because then the PDF is, yeah, like a delta function is the zero variance, right? Yeah. So many objective is one of the thing. But we will not go that route. That's an advanced optimization course we're talking about. Not even a usual optimization course does that. But if you are interested, there is NSGA 2, NSGA 3, NSGA 4, go and check it out. NSGA turns out to be, that paper was actually by Kalyanmay Deb when he was in IIT Kanpur actually. And that was, I think, the first paper from India that got more than 10,000 or some citations. First paper by an Indian author from India. Many Indians have more than 10,000 citations for a single paper, but those are authored from outside. So that was one of the paper, although he then left IIT Kanpur and now is in Michigan or somewhere. So he's no longer in Kanpur, but when he did that work, he was a faculty at Kanpur. Okay. So many objective is a way. We'll not talk about that much. But we don't want to go the many objective route. So what can we do? What can we do? We need to combine the two objectives to arrive at a single objective, right? How will you combine them? Lagrange multiplier comes when you are dealing with constraint. Two objective Lagrange multiplier will not come into play, because you are not trying to satisfy a constraint, you are trying to minimize something. So what will come into picture is some weighted sum. So let's say A times mean plus 1 minus A times variance. Now that's A parameter you change from 0 to 1. For each value of A, you will end up with a different result. If you are not sure, take 0.5. 0.5 mean plus 0.5 variance, and that will give you a balance between mean and variance. So it's not a hyperparameter, it's a design parameter in this case. You have to do it for all the A, and then the client will decide which A he or she wants. So it's not a hyperparameter, all the points are valid points that you will get, and you will leave it up to the client to decide what to take. And same kind of thing you get even in many objective or multi-objective. And what you get for different alpha, I'll show it to you, is known as the Pareto font. So yes, so I'll show it to you in a short while, but all the alpha are valid alpha. There are many solutions. It does not have a single solution, and I'm not talking about many local optima. It can have many global optima actually for each value of alpha, assuming it is convex and all those things, right? Or who has to know? Yeah, you will do it for different values of A, I said, and you will give a graph which plots A versus optima to the client, and let the client decide which value of A he or she likes or they like as a company, right? You as a designer is not in a position to take a call on what A to take. You can suggest that based on my experience, I think this A value is good. But the final selection will be done by the client who is paying you as a designer, right? So that is kind of the idea. So in RDO, you will minimize D star. And when I say D star, remember that I said that D is constant, not probabilistic, but in most cases D will be probabilistic. And in this case, D star will be mu D star. You are looking at the mean of the design variable, right? You are trying to minimize arg mean D mu of C, let's say A of mu of C plus 1 minus A of sigma C, right? Where A can vary from 0 to 1, obviously. It's a continuous number, can have infinitely possible value of A, but it will vary from 0 to 1. That is fine, okay. Now, tell me about the constraint. What will happen to the constraint? Will it remain as it is? Because it's also a function of D and X. So it is also probabilistic. How will the constraint look like? How will the constraint look like? That is probabilistic, right? But how will it look? Previously it was reliability. We will not use reliability in this case, but there is still probability there, if not reliability. So can you think of something that the constraint will look like? Distribution, how? Let's see. Distribution what? The constraint is of H. H has a distribution, I agree. But you need a function, right? So let's say distribution function is a function, but then what is the constraint? Less than equal to greater what? You will look at the worst case scenario, right? It's already a bound, one-sided bound, right? But so what do you mean by bound? Because there is already a bound, less than equal to 0 is a bound. Yeah, one side bound, other side is not bounded, but it's a bound, right? But what will you do? Think about H. What is H? Give one example of H. Stress displacement I was saying, right? So previously what was it? That stress, which is H, should be less than equal to some threshold T, HT, right? Previously it was like that. Now this H is no longer H, it's a PDF of H. So H will look like something like this, where this is the value of H and this is the PDF of or frequency of H, right? So that threshold value, let's say, is somewhere here. You don't know. I'm drawing it, but it may be somewhere else, right? So now from this diagram, can you say what should we do? Less than? What is less than HT? CDF, that is probability. We are going to reliability. We will not go into reliability, right? We'll look into the bound of the PDF. The PDF has a bound. For example, let's take Gaussian. We know Gaussian varies practically from mu minus 3 sigma to mu plus 3 sigma. Theoretically from minus infinite to plus infinite makes no sense, but practically mu minus 3 sigma to mu plus 3 sigma. We know that. So can we not write in this diagram, look at it, that mu of the h plus 3 times in this case sigma of h should be less than equal to the threshold. That will ensure the safety also without doing reliability. Right? So the constraint will be mu of h plus, I told 3, I will not write 3, that number 3 can change based on distribution and all those things, so it should be k times sigma of h less than equal to 0, the threshold was 0 in this case, so 0, right? Obviously in this setup you can imagine that I am assuming that h will be positive, right? If h is negative or mu of h is negative, then that plus in between should be negative. Then it should be mu minus, because in that case the lower bound starts mattering, right? In that case, you can imagine. We have to give. We have to give based on your knowledge of the system, let's say. For example, in most cases this k is 3 because we assume it to be Gaussian, and that is a safe option, I will say. But if you want an even safer option, take 5, 6. The more higher value you take, it's like a factor of safety kind of thing, not factor of safety, but like that. The higher the value, the more safe it is, right? That is the idea. So this is what we will do. Mu of h plus sigma of h, k times sigma of h less than equal to 0. And if this is going to, I mean, in this case, it will never go to negative because the constant is less than equal to 0. That means the mu is on the positive side, right? But in the other way around, sometime it is a greater than equal to constant, then it should be negative and all those things. You should be careful. It depends on the type of constant you have.
A will be also a part of this optimization.
Yes. Yes.
So this will
But A will not optimize for A will set, and you will get different values of this star for a given A. Correct. Okay. So you will not solve it. You will get different values of D for a selection for a A that you select, and then you plot that for different A and give it to the client that okay, here is your design, choose one, right? You are giving options, right? Is this fine?
then we put that in the name of approximate minimization.
So first you will minimize the, very good, then what, why different standard deviation? You will get only one standard deviation. Minimizing the standard deviation means A equal to 0. So you get a single D in that case. I mean this, whatever you said initially, right? Minimizing the standard deviation. All the value of what?
Like here we have one standard deviation for the green part.
So this D will be 1000 dimension. So you will compute 1000, you will try to visualize that in 1000 dimension. Is that you are suggesting? I mean, this is 1D I will drawing so that you can visualize. This will not be 1D. I mean, what you are saying is correct, brute force. Why not we sample D, right? Compute variance and mean at all the D's, and then take the mean of that. That's the brute force optimization you were saying. That's the Monte Carlo, right? Way of doing things. You can do that. There is no guarantee that will give any meaningful result, but that's a possibility, right? That's a brute force optimization, right? which always works. Maybe we will do that once quantum is there. Once quantum is there, maybe that is what we will be doing. We will be going to the brute force way, doing things in qubits and all those things, right? Maybe that is the future, who knows? But right now, that's not. Okay. This is clear? Okay. So this is your RDO problem statement, right? Obviously, the limit will also be there, the D limit, and that will not change in most cases, but it will be there. You can imagine the limit can be changed, the D minus mu of D minus 3 times sigma of D should be less than equal to lower limit, or and then plus is greater than equal to upper limit. You can also do that, but that is quite straightforward. Once you understand H, you definitely understand what you are supposed to do with D, right? So yeah, so this is the RDO's problem statement, and you can imagine that this is quite different from the problem statement of RBDO. In RBDO, the objective function was deterministic. At least the RBDO that we discussed, right? But in this case, the objective function is probabilistic. But now, this is only one type of RDO. There are other problem definitions of RDO. So can you think of any other problem definition of RDO? So robust, the term robust might have different meaning actually. One meaning of robust is what we are going by, that it should be insensitive. The other meaning of robust can be it should never fail. That's why my design is robust. No matter what you do, it will not fail, right? That is another way of looking into things. So from that point of view, can you come up with another problem statement for this RDO? Someone is saying min max. So can you think of in terms of min max? So C, right, is the objective function, correct? C now has a PDF. Can we not maximize, the value of the PDF, and not the value of PDF, the maximum value it can take, and then minimize that? So minimizing the worst case scenario basically. Maximize the response, so you draw sample, take the maximum one and try to minimize that. Because it's a PDF. So let's say it's a PDF, mu plus 3, 0 mean, 1 standard deviation, let's say. So then practically it varies from -3 to +3, right? So find the D so that the +3 reduces, worst case, right? So that will give you a min max kind of formulation where you minimize the maximum of F or minimize the maximum of C in this case. And C will have a maximum and minimum because C is probabilistic, it's random, right? So you can also imagine an RDO formulation which uses a min max formulation, and these two are very different. It's not equivalent, they will give different results because both has different meaning of robustness. One is saying robustness means that even if D changes, it will not vary. The other is saying even if D changes, I have minimized the maximum, the worst case one, it will not fail. Two are very different definition of robustness, but both comes under the RDO framework. That is also the costly one. Better in what sense? In safety sense, you are right. But is that the economic one? No. So when you say better, again, that's a multi-objective, right? Yeah, so that's also a multi-objective. Better in what sense? Safety and cost, right? Yeah. That is used in many cases. That is used actually. Okay. But this one is the more popular one. In RDO literature, this one is the popular one. People use it more, much more than that one, but that also exists. In fact, people also use only expectation. Alpha equal to 1 or A equal to 1. That's also RDO design, but that's not the best RDO design. But people uses it. Correct. It won't be insensitive. You're right. But people uses it with the idea that okay, that's fine because I have this K in my constraint, which is generally my safety thing, and because of that K, it will still be safe. Obviously, it is not robust, but people use that because people say that that's a special case of A, right? A equal to 1 is a special case. So in some places you will see that they called that also a robust one. In some places they will call it the probabilistic optimization but not use the term robust. So there is argument and discussion over that as well. Okay. Any doubt on this one? Is the big picture clear of robust design optimization and reliability based design optimization in general, right? So last day I was also talking about robust reliability based design optimization. What will be the problem statement in that case? The objective function will be as it is, A times mu C plus 1 minus A times sigma C. But the constraint will not be plus K, but will be reliability constraints there. Probability that but H less than equal to or greater than equal to some threshold is less than equal to very small number. And that will make it a robust reliability based design optimization. All these three you can imagine are designed under uncertainty frameworks, but each looking at the problem from a different lens. Actually two, I always tell it two, not three. So one looking from the robustness lens, one looking from the reliability lens, and then you combine them, get the third one, but that's not really a new one, right? That's a combination of the two, right? Same thing, Lagrangian will come. Yes, that will not change. Once you've written down the problem statement, now the optimization remains as it is. Okay. By the way, what is the cost of this? I mean, is it, not exact cost or order of computing, but do you think it will be as costly as RBDO, or is it more efficient, less efficient? What do you think? Less, more efficient than RBDO, not for obvious. DDO is the most efficient one. I'm not going there.
Getting the maximum output, not that it's a good kind of
Okay, let us go one by one. Why do you think so? Just defend yourself.
output. Less fluctuation. Like I have studied the problem of wind turbine system. Wind is going from different directions, within the level of maximum output. But some sense it's the
That's a different thing. I'm saying computational cost. Why is it more efficient? You said it is more efficient, right? Computationally, why is it more efficient? Because you said it will be more efficient, right? You don't think it will be? Yeah, you were saying need not be. It's a trade-off, you said.
Cost will increase, but not that much. But we will get a
Why will not that much? I'm not interested in accuracy, only efficiency. Why not that much? How will you write a code? Think about that. You will have an outer loop of optimization. That will be there. There will be an inner loop, but inner loop of what? Of computing the statistics, mean and sigma. You need to compute the mean of cost function, mean of H. You need to compute the sigma and sigma. So there is a inner, it's a nested loop, at least by definition. So that part remains the same. Previously the inner loop was computing reliability. Now the inner loop is computing statistics. So now the question the outer loop remains the same. So the question boils down to whether, how will you compute the statistics? Best way is sampling. Let's consider sampling in both MCS. So I'm using MCS to compute the statistics, mean and standard deviation. I'm using MCS to compute the reliability. Which one is more efficient? Why? Here also this is to solver only. H is trace. So solver will run for each X. You will get a sample. You are getting it through solver only.
outside and surrounding.
You cannot, D is sitting there. Surrogate to anyways we can do there also. We are not going to surrogate. We have to keep it apple with apple, right? So both places MCS. Now think. Don't say that one place I will use importance sampling. Then I'll say don't use importance sampling in reliability. That will be more efficient. Whatever you will say, I will reverse it. And the other one will become more efficient, right? Less number of samples for which one? For reliability or for this one? Why?
There we are calculating probability of failure.
Right?
It happens so that we have to take so many samples to finally see.
Why? Let's look at this diagram and now try to explain. This diagram will tell you. So what do you actually compute in a PDF when you compute the probability of failure? You compute the tail of the probability. Because there is a threshold and beyond the threshold is what you are looking at. So that's a very small area. Right? Which means most of the samples you will draw will be in the not in the failure zone, which will be anyways be ignored. Which means that is why you need lots of samples. And we know that the more smaller the failure probability, the more the sample you need, because the original samples are spread all over the PDF. As a result, the number of samples needed for computing probability of failure in a realistic sense, which is 10 to the minus 3, minus 4, minus 5, is much larger than the number of samples that you will need for a acceptable range of mean at least. For mean, generally 1000 to 5000 samples is enough. Unless and if you are able to draw the samples properly, obviously. For variance, maybe 10,000 is enough. Because it's a global measure. So the correct terminology is that mean and standard deviation are statistics. These are global measure. Whereas reliability is a local measure. It's a tail. It does not concern the overall area. Mean and standard deviations are global measure. It tells you everything about, not everything, but it gives you information about the overall PDF, right? Behavior of the overall PDF. The tail does not. It only gives you about it. So it's a local measure. And because it's a local measure, most of the samples are anyways in a useless area. And so the number of samples required for computing reliability is generally more. Generally, I'm using because you can say, okay, I'll design for 10 to the minus 1 probability of failure. Then though it doesn't matter, right? So, but then there is one more thing. Reliability design optimization is solved only once. RDU will solve for different values of A also. So the comparison I was making was for 1A. But you will do it actually for different A. But again, you can say I will do it for 10A and I will parallelize it. That is equivalent to going for 1A. Yeah. Obviously. Correct, but as I said, apple to apple. So in this case, you should use Potter version here, because mean and standard deviation you can get from Taylor series as well. I mean, in real world, you actually use form. You cannot use the other one because of computational cost. It will not be accurate, is what you are trying to say, and I agree. But it's not that you cannot use it. People are relying on that, because the other things actually you cannot use because of computational cost. But yeah, so coming back to that, we will use Potter-Besson, which means Taylor series up to first order, and then take the mean, and same cost. Then it's the same cost. Actually, a little bit more cost in reliability still, because then there is an inner optimization also for finding out beta. Whereas for statistics, there is no optimization. Closed form, we will get the mean and standard deviation, right? So yeah. C and H both. So the objective functions mu of C, right? You will take C, expand C in terms of X and D with respect to, let's say, mean. So C at, we want mu H and sigma H. We want mu C and sigma C. So I will take C and H. Look at the left hand side. C and H, I will do a Taylor series expansion and take the mean of that and take the variance of that, standard deviation of that, and that will solve it, right? That will give me mu C, mu H, sigma H. All. H also I will do the Taylor series. H is also I will do Taylor series, right? Like how will you find out probability of reliability? We'll do Taylor series, same thing. It is true though that you have to do 2 Taylor series here and 1 Taylor series in RBDO. But still, this will give you closed form. So it will not matter, right? Okay. Clear? Okay. But the point is that it's still expensive. It's still nested, at least till now. Right? There is one more problem here, and for this I want to wrap it up, the RDO one. I don't have time, so not today maybe, but next lecture I will wrap it up. But the problem here will also be to compute the gradients, because you will need to compute gradient with respect to mu C, or gradient of mu C with respect to D, gradient of sigma C with respect to D, gradient of mu H with respect to D, and gradient of sigma H with respect to D. How will you compute those? We'll talk about it in the next lecture. And that will actually allow us to go from, we'll try to decouple it. I already gave you some clue how you can decouple it based on what his question actually. So that is the way of decoupling this. We'll make it a single loop with the form or the Potter-Besson method. We'll do it next time. But with Potter-Besson method, you will see that you will not need the inner loop any longer. Do the Taylor series, that will automatically give you the mean in one go. You just have to play and plug and play. Okay, we'll see it next time. I'll not do it today, but I don't have time, right? I have 2 minutes. So that is the idea, okay, of RDO. So next lecture, we will wrap up RDO by looking into 1 or 2 algorithms of this. We'll talk about, we'll write down the algorithm of the nested one first. From there, we'll go to Potter-Besson, how you can do it using Potter-Besson. From there, we'll go into or tell you briefly about the stochastic simulator idea. That is directly applicable here. The stochastic simulator, I think your project is on stochastics. So that is directly applicable here, and I'll talk about that also. And we'll wrap up our discussion on RDO in the next lecture. So next Wednesday, there will be a shorter lecture. Maybe 30 to 40 minutes is what I will take. I have a flight to catch after that. And next Thursday, there will be no lecture. This Saturday is a working day, there will be no lecture. I will not take any Saturday. Okay. Which means I will miss a class, which is fine. One class I missed earlier, so I will take one extra class sometime, maybe in the evening. And that will be a 1 hour class for both of this missed one, right? But not 2 hours. And my expectation is that RBDO will be done by next RDO. This designer optimization will be done by next week. So next week is 27, so end of this month, right? So next month we will be left with system reliability and time domain reliability, which will not take more than 2-3 lectures. Okay. So we'll be done before time actually. We'll stop at before that. Your project presentation is coming, obviously. It has to be there. So my plan is to have a 1 day kind of project presentation, maybe on a Saturday or something like that. Let all of you present on a single day and get done with it. Okay. And it will most probably be before the majors. Maybe the classes that will be remaining during that. So before 14th event. Let us see how it goes, but that is kind of the idea, to get done with it before the majors itself. After the major, there is only one thing that will be remaining, that is homework 5. Because that deadline is after the majors, right? Okay. So that is the idea. Next week we will wrap up with design under uncertainty. And then the week after that, we'll start with this system reliability. Time dependent, if I'm not covering, I'm fine with that. System reliability, I do want to cover. So if time does not permit, I will skip time dependent reliability. That is anyways a very big topic, and sometimes you need to do a course on vibration, and not all of you have done on vibration. At least the UG students, I know that you have not done a course on vibration. So in that case, I will give you broad idea of that, but I will skip that. System reliability, I do want to cover in details. So system reliability will do in details. Okay. Thank you.